Identifying a problem or need, researching potential solutions, and selecting the best one based on defined requirements and restraints is the engineering process. We will use 4 fundamental steps in the engineering process to create a prototype wing. We'll start at the conceptual stage with our design brief. This details the criteria of the wing. We will refer to this information frequently throughout the project to ensure that we do not deviate from the brief. To model our wing within limitations, we use Euler-Bernoulli's beam theory to determine the maximum tip deflection and derive an equation that correlates tip deflection with factors point load, spar length, Young's modulus, and the second moment of area. We also considered torsional compliance by simplifying equations to assess the wing's ability to withstand twisting loads by assuming deflections are moderate. The spreadsheet started by inputting design specifications from the briefing document and estimated foam board properties to generate an initial spar design. The spreadsheet tool provided an initial understanding of stress changes along the beam's length, aiding in predicting the greatest load application and predicting potential beam failure areas. The spreadsheet helps create a first draft cross-section of the beam by calculating the beam's ability to withstand the moment produced by the wing structure, torsional forces, and deflection along the wing. It is critical that the spar fits within the wing profile. This tool aids in displaying and avoiding problems caused by the spar protruding from the aerofoil. We trialled several spar revisions to find a design that prevents this problem. The spreadsheet provides all dimensions and information for our wing, which can be used to design it in CAD before physical prototyping. This saves time and money by allowing for iterative design changes due to discovered issues. CAD models are also useful for showing how parts work together before physical prototyping, allowing us to test compatibility between parts. We also need to model in CAD how we will physically test the prototypes. This contributes to the simulations being as real as possible. A completed CAD model can be tested using computational simulations to ensure its behaviour aligns with the design brief. However, the spreadsheet does not validate the accuracy of the simulations. When testing physical prototypes, results should be compared with the simulation's outcomes to validate their accuracy. To obtain precise results for comparison, we must ensure the build quality so it does not deviate too much from our simulation. We also need to use the same materials as we did in our simulations. We started by bending the spar horizontally in a table vise and taking precise measurements with a vertical ruler and set square. The torsion test involved the attachment of a ruler to the cross-section of the spar, followed by the attachment of masses to the end of the ruler, and subsequent readings taken using the same method as the bending test. Our bending moment simulations closely matched our lab tests, with differences of less than a millimetre. This minor variation could be due to inconsistencies in the adhesion between foam sheets and minor flaws in the sheets. They are minor enough that they could be due to measurement errors caused by simulation's higher accuracy in measurements. The torsion simulation closely matched our lab results, with minor differences likely due to similar reasons. Looking back at this project, you can see how the engineering design process took us from just a set of requirements to a built and tested prototype wing.